everybody, welcome to video 2 of our SN2 versus E2 versus SN1 versus E1 comparison. And so what I'd like to talk about now is the factor that the concentration of the attacking species has on the selectivity between these four mechanisms. So if we look at our two rate laws, so SN2 and E2 we can group together as long as we say attacking species and not nucleophile versus base. And then we can group SN1 and E1 together because they have, for all intents and purposes, the same rate law. We can see that a strong concentration of, a high concentration rather, of strong attacking species favors the SN2 or E2 reaction by speeding up the rate. So essentially we're forming these products faster with this mechanism because there's a high concentration of attacking species and the concentration of attacking species is directly proportional to the rate. On the other hand, a low concentration of strong attacking species or a weak attacking species itself will wind up favoring SN1 or E1, not necessarily because this makes the SN1 or E1 reaction faster, but because this slows down the competing SN2 and E2 reaction. So in summary, high concentration of strong attacking species will favor SN2 or E2, and kind of a crappy attacking species, so something like water, something like methanol, is going to wind up favoring this SN1-E1 stepwise type mechanism, and we'll see why that is in a few seconds. Okay, so what you should probably do now, pause the video, finish writing this down, and then when you're ready, unpause and we'll start talking about how the nature of the leaving group, so basically the type of leaving group on the electrophile, can influence whether we're going through this SN2-E2 mechanism or whether we're going through this SN1-E1 type mechanism. So welcome back. The third control lever we have for this SN1 versus E1 versus SN2 versus E2 is the nature of our leaving group. And so what I've done here is, again, I've wrote up our rate laws here for the SN2-E2 and the SN1-E1. And what we can see is that for the SN1-E1, we know for a fact that the nucleophile doesn't play a role in the rate determining step of this reaction. And so while we know that this means that if we increase the concentration of nucleophile, we're not going to change the overall rate of this reaction, what we can also think about is that, okay, in this case, our leaving group has to do all of its leaving by itself. There's nothing that's going to be able to assist it. It simply has to take the electrons and leave. And so what this means is that really strong leaving groups, or really good leaving groups, tend to play a big role in allowing the SN1 versus the SN1-E1 mechanism to take place. On the other hand, if we look at the rate law for SN2-E2, we can see that because our attacking species is present in the rate, we know that, first of all, high concentrations of this attacking species makes it go faster. But we know from our FMO analysis that part of the reason that our leaving group leaves, so in other words, why we break our carbon leaving group bond, is that we are actually occupying the anti-bonding orbital of the carbon leaving group bond, meaning that we're essentially causing that bond to break with a little bit of help. And so we can think about this here in that, for an example, we have a reaction between this hydrosulfide anion and this iodomethane electrophile. We can see that the way in which this SN2 reaction takes place, let me just grab my pen, is that we're going to take these electrons and put them in that sigma star orbital. This will form both our new carbon-sulfur bond while at the same time kicking our leaving group out. And we see the same type of thing happening for an E2 reaction, where we wind up having some sort of base come and pluck off a proton. And what that means is that the electrons that are in this carbon-hydrogen bond are free then to overlap the sigma star orbital, so essentially the anti-bonding orbital of the bond holding the leaving group to our carbon, causing that to leave. And so what this means in this case is that the nature of the leaving group, so whether our leaving group is spectacular or just okay, is not a big of a deal with an SN2E2 reaction as it is with an SN1E1 reaction, where the leaving group has to completely leave of its own volition. And so if we want to favor an SN2E2 reaction, your book will actually tell you that, you know what, you can actually use a poorer leaving group in order to favor this. In practice, this is something that chemists don't really do a whole lot. There are better ways to favor SN2E2 versus SN1E1, specifically through strength of nucleophile. And while a poor leaving group is more likely to go through this SN2E2, it is also more likely to make your reaction slower. So while your book will tell you this, take that with a grain of salt, because in all practicalities, you want to make sure that your reaction is both selective and happens at a reasonable rate. Nobody really wants to sit in lab for 9 hours waiting for an SN2 reaction to happen. Trust me, been there, done that, not fun. So where we'll pick up in the next video is that we're going to talk about some additional information about leaving groups. So what makes a good leaving group, and we're going to do this with a little bit more specificity than simply, okay, a good leaving group is a weak base, but also, when we have a poor leaving group, are there ways that we can convert this to a good leaving group? See you in a couple.